Hey there, welcome to Chapter 8. I will be breaking Chapter 8 down into I believe three lessons, unless they get too lengthy. And then I might need to subdivide further. But the first one will be focusing on bonding in general and ionic bonding in particular. So what is a bond? Think about that for a minute. Keep it simple, don't overthink this. Simply put, a bond is nothing more than a connection between particles. There are different types of bonds. The connection is different in those bonds. Okay, but that's really all this is a connection. What causes a bond to form is atoms getting close enough to interact with one another. Because atoms interact, and because the nuclei of atoms interacts not only with the atom's own electrons, but any electrons on neighboring atoms, bonds will form, or may form, when atoms get close enough to feel that interaction, that attraction between electrons and the nucleus of neighboring atoms. I hope that you have heard of this property of atoms known as electronegativity. This figure here comes out of your book, figure 8.8, and this shows electronegativity values. Now, we probably ought to define electronegativity before we get too much farther. Definition of electronegativity: the ability of an atom in a molecule to attract electrons towards itself. Okay, so it's a tug on electrons by an atom that is sitting next to other atoms. Okay? Do you notice anything missing in this sort of periodic table of electronegativity values? I hope you do. If you look closely, you will see that the noble gases are not included in this table. And the reason for this is that noble gases don't particularly bond with things. They are known for their poor reactivity, and so most electronegativity tables do not include the noble gases. I have seen some that had some values, but it's not the common way that you're going to see this table. The way to determine the kind of bond that will form between a pair of atoms is to examine their electronegativity difference. If there is no difference between the electronegativities of the atoms in the pair, then the atoms will share the electrons evenly between them. This is known as a nonpolar covalent bond. Okay? If there's a small difference in the electronegativities of the elements, then we're probably going to have a sharing, but it will be an uneven sharing or a polar covalent bond. As the difference increases, the bond becomes more polar, and as the difference is less, the bond is less polar. If the difference becomes large enough, there is no sharing. Instead, there is an electron transfer from the atom with the lower electronegativity to the atom with the higher electronegativity. And this is always going to be the metal will lose the electron, the nonmetal will gain. Now, to quantify this, let's look at actual difference in values. The difference between the electronegativities of carbon and hydrogen is actually only about 0.4. And that is actually so small that I'm going to put this bond in the nonpolar category. It's just about borderline, okay? But such a small difference that it really doesn't amount to much unevenness at all. As we get to larger differences, if we reach the point where we have a 1.8 cutoff, if you're greater than a 1.8 difference, the bond will be ionic, this transfer we're talking about. And if we're less than 1.8, it will be polar covalent. That's kind of an arbitrary cutoff. Some texts will use 1.7, 1.9, 1.8 is a good value for us to stick with for this year. So let's actually look at ionic bonds and define those carefully, okay? An ionic bond is not a transfer of electrons. An ionic bond is what happens after the transfer of electrons, okay? So a transfer of electrons happens, and then the particles kind of glom together because they're positive and negative. I'm going to use Na and Cl as an example. Na has 1 valence electron. Cl has 7 valence electrons. What I'm using here is a Lewis dot structure to show valence electrons and what might happen to them. Okay? In this case, sodium has an electronegativity value of 0.9, and chlorine has an electronegativity value of 3.0. The difference between these electronegativities is 2.1, which is certainly above the cutoff for sharing. And so what will happen here is if these atoms get close enough to each other, they have to get a little closer. And what will happen is the chlorine nucleus with a stronger pull on electrons will actually snatch the electron away from sodium, resulting in a sodium that is a +1 cation and a chloride -1 anion. And because this will happen with thousands of sodiums and thousands of chlorines doing this all at the same time, the result is that we will create a crystal lattice network of alternating positive and negative charges. Notice what I've sketched here is two-dimensional, but if you were to take a look in your textbook on page 302 at figure 8.4, you will see a more three-dimensional crystal network for sodium chloride that shows how dozens of sodiums and dozens of chlorides arrange themselves in this alternating network. And that crystal is held together not by shared electrons, but by the force of attraction between positives and negatives. Let's look at an example of calcium and chlorine approaching one another. The electronegativity of calcium is 1.0, chlorine is 3.0, so I have a large enough difference. What's going to happen here, though, is chlorine can only take 1 electron from calcium, and so the ratio on which these would combine is not going to be 1 to 1, it's going to be 1 to 2, resulting in a compound with calcium cations 2+, and 2 chloride ions 1-, or a formula of CaCl2. In the case of magnesium and oxygen, there is a large enough electronegativity difference so that if these atoms get close enough, the oxygen will snag actually both electrons of the magnesium because it has space for them, making the formula MgO, in this case a ratio of 1 to 1. These are formulas, okay? We are not writing Lewis structures at this point. I'm showing electron movement, that's what I'm doing here, showing electron transfer, and I'm resulting in a formula, but I'm not drawing a Lewis structure for ionic compounds. Lewis structures are reserved for compounds that have covalent bonds in them. If you have taken physics, I think it's likely that you will have heard of or used Coulomb's law, okay? And your textbook has a sort of almost the same variation for the force of electrostatic attraction between charged particles. Coulomb's law, I think, is really the way we ought to go with this. You can see that they're very, very similar. Q1 is the charge on one of the ions. Q2 is the charge on the other ion. And R is the distance between those ions. This is the force of attraction. And K is a proportionality constant. It's not a number you're ever going to have to use in solving anything. And it would be a constant in all examples. So if you look at this law and think about what it's telling us, you should be able to understand how changing the charge and changing the distance would alter the force of attraction. So I think you will agree with me that as Q increases, the force of attraction between the oppositely charged ions would increase. If Q decreases, the force would likewise decrease. If R increases and the particles are farther apart, the force is going to decrease because R squared is in the denominator. And if R decreases and the particles are closer together, the force is going to increase. That's a very important relationship to understand. So make sure that you understand how that works with the equation that we call Coulomb's law. So here's an important table that comes right out of your textbook in Chapter 8. And we're going to talk about what these lattice energy values mean. First, a definition of lattice energy. Okay, this is essentially bond energy for ionic compounds. It's the energy required to break up the crystal lattice and pull the ions apart, or the energy released when the ions come together to form the crystal lattice. In explaining the difference here, we should look at the ion sizes. The sodium ion is the same in both compounds, but the fluoride ion is a smaller ion than the chloride ion. And what that does is, in Coulomb's law, it decreases d squared, which causes the force to increase. So in this case, the d is changing, Q is not changing. We will make some other comparisons of ion sizes and study the lattice energy in a little more detail in class.